In number 8, we are to graph the polynomial function, locate its extrema and zeros, and explain how it is related to the monomials from which it is built. The first thing to notice about this function, if you were writing it on your paper, obviously I've put it on the study guide for you here, but you notice that both of the x terms are raised to even powers. So if we prove that this was even, we would plug in negative x into both of those spots, but a negative x to the fourth power or a negative x to the second power would just be positive versions, so we could just drop the negative. So in other words, we've proven that the function is even by doing that. And that becomes important because we can use symmetry to save ourselves work on this first part. So if we use whatever means our calculator gives us to determine the value of the zero at the leftmost zero, which would be there, then we determine that the x-coordinate there, so our first 0, and let's just put a place to write them down here, x equals, or no, let's not say equals because these are going to be decimals, x is approximately negative 1.58, and that's the first one, and then if this thing is even, then that point has to be 0, so you don't really have to figure that out. And then, well, that's not really true. The fact that it's even doesn't guarantee us that, but 0 to the fourth power minus 0 to the second power is 0, so that one is 0. And then our third 0, we don't need to compute because we know this function is even. It has to be positive 1.58. So we've got our zeros. Well, now we want our extrema. And we have 3 extrema, so let's erase the dots for the zeros and focus on the extrema now, which are these 3 points. Well, the 2 points at the bottom have the same y value, which we know because this is an even function. So we can start with them by saying we have an absolute minimum. I don't know what happened to my n there. My absolute minimum of the y-coordinate at these 2 points, again using your calculator to compute that, you would find that you get something in the vicinity of negative 3.13 at, and it will be at reflected values of x, which when you use your trace or other technique to determine it, you get your x-coordinate for free there. X is approximately 1.12. So we've covered the zeros and extrema part of this problem, which is sort of old news, or should be at this point. So now we are to explain how the graph of g of x is related to the monomials from which it is built. Alright, well, when you completed page 2 of your study guide, you had some pairs of functions to graph and compare, and if you did not write this, and maybe you wrote it but in another way, what I want you to know about these relationships is that the weak function, or term, let's call it a term, the weak term wins, and obviously that's kind of a paraphrasing of what it's mathematically doing, but it wins in the middle. And the strong term wins at the ends. And the best way to explain what I'm saying is to look at the graph of g of x in the same window with the graph of 2x to the fourth and negative 5x squared. And that's what we have here. So when you look at this graph, you see the red graph, which is 2x to the fourth, the black graph, which is negative 5x squared, and the blue graph, which is our g of x graph. And in the center, your negative 5x squared, which is the weaker term here, and when we say weaker, we're really just talking about the lower power. So since we have a negative 5x squared, it's going to dictate more about what the graph does close to the y-axis, which is why the closer you get to the center, the harder it is to distinguish the black graph from the blue graph. But then fairly quickly as you move away from the center, what the blue graph is doing looks more like what the red graph is doing, and if you zoomed far enough out, they would look like they intersect. They would get so close, or they become one at some point if you zoom out far enough. So remember, the weaker function or term that is used to add or subtract together with another function or term to make a new function is going to have more to say about the middle, and the stronger function used or term used will tell you more about what's happening at the ends, and in particular end behavior, which becomes a very important concept for this course. Then we move on to number 18, and we're told to graph the function in a viewing window that shows all of its extrema and x-intercepts. Well, let's stop and think about that for just a minute. We have this f of x written in factored form, and remember that all I need to look at to determine how many extrema and intercepts I have is the degree of the function, and that if I know a, I also know end behavior. So let's just look at what would happen as a sort of a bulleted approach to this problem. Let's start by saying, well, I know that it's cubic. And how do I know it's cubic? Because I have a linear x factor times a linear x factor times a linear x factor. So the fact that it's cubic, I know that I have, at most, n minus 1 or 2, in this case, extrema, and at most 3 zeros. N zeros is the way the rule goes. Alright, so the reason you need to know that is that let's say you graph something and all you see is like what looks like almost a vertical line, then you need to zoom out until you can see the right number of extrema and zeros for the degree of the thing you're graphing. So that's a little tip for that. But we can also predict end behavior, and you can either pause the video now and then graph it, or listen to what I'm saying now, but this should make sense. The other part of the directions tell us to describe the end behavior using limits, and the only acceptable proper notation is to write the limit as x approaches negative infinity of f of x equals. Well, if we were thinking the way I asked you to think a moment ago before we were to graph this, about what the leading term should look like, it's going to come from the leading term of each of the things being multiplied. So it would come from 2x times negative x times x, which would imply that our leading term is going to be negative 2x cubed. Now, the reason that's beneficial to know is that I know that this is going to act like the cubic graph but upside down. Well, the parent cubing graph, the limit as x approaches infinity is infinity. The limit as x approaches negative infinity is negative infinity, but this one is upside down. So for our graph, as x approaches negative infinity, our graph will approach positive infinity. And the limit as x approaches positive infinity for our graph, which would be the reverse vertical reflection of the parent, this one will go to negative infinity because it's upside down from the parent. Now let's look at number 24. Same set of problems, different problem because this one's written in standard form, but we can use the same kind of an approach before we graph it, or if we need to make sure we're seeing all of the significant points in the window, we can take note of the fact that this is a quartic or fourth degree, and I will write both here. And that is terrible writing, so let me fix that. Quartic implies that I will have at most, and you can have less than this, but no more than this, at most 3 extrema and 4 zeros. So you need to know that going into your calculator, otherwise you'll come up with some silly conclusions. But again, I really don't need a graph if I know my leading term test, and our leading term is negative 3x to the fourth, so I know that because it's negative 3x to the fourth, it will behave in a vertical reflection of its parent, x to the fourth, which would look, at the ends would look like a parabola, but it's going to probably be a little flatter in the middle. That's a pretty extreme exaggeration there. But this would be the parent, so then since I have a negative leading coefficient, then I know that we're looking at something that's going to be upside down. So then I know for my end behavior that the limit as x approaches negative infinity of this f of x is going to be negative infinity. And if I'm thinking, because this, if I've just sketched that picture to think it out, I know that they're the same, so I can actually say, let me erase so I got room to write it. I can collapse this into one statement that these are both going to be at negative infinity, so I can say as x approaches either plus or minus infinity, the limit is negative infinity, which you can always do with an even function. And I do not know why my board is not wanting to make that box around my limit there. And that's number 24. On to number 26, the final example for this video. This set of problems takes you out of the whole having to graph it first, and I think that's the author's just trying to help you get comfortable with realizing that you really only need to look at your leading term, because these directions say describe the end behavior of the polynomial function, and it uses symbolic representations of limit notation to tell you to write your answer as limits. Well, pretty much what you need to get in the habit of thinking is that the parent graph, so for this one, because it is a cubic polynomial, would be x cubed, and you know that the parent looks roughly like this. It goes down to the left and up to the right, and then think about the fact that you have, so that's your first step, but then you got to go to the thinking about the fact that your a is negative 1, which is going to reverse that graph vertically, flip it vertically, and so it's going to look roughly like that. So then I don't need a picture, a specific picture of this graph to verify that I'm right. So for this function, my answer is the limit as x approaches negative infinity of f of x is positive infinity, and the limit as x approaches infinity for f of x equals negative infinity. And that is the answer to that one and the end of this video.